All right, so let's get started with chapter 4, software architecture. This lecture will cover 4.1, why is software architecture important? And 4.2, architecture design. I'm also going to go over various models of software architecture in this lecture. So to create a reliable, secure, and efficient product, you need to pay attention to architectural design, which includes its overall organization, how the software is decomposed into components, and the server organization. The technologies that you use to build the software, the architecture of the software product, and its effects. So you're looking at performance, usability, security, reliability, and maintainability when you're looking to develop a software architecture model. So there are many different interpretations of the term software architecture. Some focus on architecture as a noun, the structure of a system, and then others consider architecture to be a verb, the process of defining these structures. So now let's look at the definition of software architecture by IEEE, which is the industry standard community in engineering. So their definition says architecture is the fundamental organization of a software system embodied in its components, their relationships to each other and to the environment, and the principles guiding its design and evolution. So a component is an element that implements a cohort set of functionalities or features. We've been talking a lot about functionality, we've been talking about features, and so that is housed within a component. A software component can be considered as a collection of one or more services that may be used by other components. So when you're designing software architecture, you don't have to decide how an architecture element or component is to be implemented. Rather, you are designing the component interface, and you'll leave the implementation of that interface for a later stage in the development process. Architecture is important because the system has a fundamental influence on non-functional system properties, and we'll take a look at those in a moment. But it involves understanding the issues that affect the architecture of your product. And that's how you will look at these principles to decide which architecture model that you want to use. So before we go into that, let's look at the top 10 architectural patterns. So before major development even starts, we have to choose a suitable architecture that will provide us with the desired functionality and quality attributes. So therefore, you should understand what types of patterns are out there before you even pick a design and way before you even start coding. So let's look at these individually. The first one is a layered architecture. Your book refers to it as service-oriented architecture. So layered architecture is a way of organizing the structure of a single system. It can be a service-oriented architecture, but you can use a layer for more than just service-oriented architecture. We'll see in the next lecture, the example we've been using throughout the course, iLearn. So iLearn is an example of a layered architecture. So what is it? This pattern can be used to structure programs that can be decomposed into groups of subtasks, each of which at a particular level of abstraction. Each layer provides services to the next higher layer. And so there are 4 common layers that are used. There's the presentation layer, which you see as the user interface. There's the application layer, which is known as like the service layer or where the application resides. Then there's the business logic layer, that's known as the domain layer, and then the data access layer, known as the persistence layer. So some applications that have a layered is general desktop applications and e-commerce applications. Next is client server. Again, the book refers to this as a distributed architecture model, but the client server architecture is a type of distribution architecture that is suited to applications where clients access a shared database and business logic operations in that data. In the architecture, the user interface is implemented on the user's own computer or mobile device, and functionality is distributed between the client and one or more service computers. So the pattern serves and consists of two parties, a server, a client, or multiple clients. So clients request services from the server, and then the server provides relevant services to the clients. So some use cases, you see this in online applications, such as emails, document sharing, and banking. Next, we have multi-tier client service architecture. This is just a different view when you have different levels of servers on there. So it's still a client server, but just different, a multi-tier view. Then you have the service-oriented architecture. In this, these are stateless components, which means they can be replicated and migrated from one computer to another. So you have many servers are involved in providing services in a service-oriented architecture. You hear a lot about the model view controller pattern, also known as MVC. Model contains the core functionality at the data. View displays the information to the user or more than one users. And then controller handles the inputs from the users. This is done to separate internal representations of information from the way information is presented to and accepted from the user. So a client server uses MVC communication, such as HTTP protocol. And we'll talk more about this in microservices architecture lecture. But you have requests such as get, post, read, delete. Okay, and so these commands are done by the controller, which you have your input events from the view of the user. So this model is useful for the World Wide Web applications, of course, and major programming languages, web frameworks such as Django and Rails. And yeah, so that's the MVC. Then you have the master-slave model. This pattern consists of two parties, obviously your master and your slaves, and the master component distributes the work among identical slave components, and that's the key, identical components, and computes the final results from which the slaves return. Okay, you see this in database replication, where the master database is regarded as an authoritative source and the slave databases are synchronized to it. Next, we have pipe and filter. This pattern can be used to structure systems which produce and process a stream of data. Each processing step is enclosed with a filter component, and data can be passed through the pipes. So you see this mostly in compilers. When you're trying to build a compiler, the consecutive filters perform lexical analysis, parsing, semantic analysis, and code generation. You also see this work in workflows in bioinformatics. Next, you have the broker pattern, and this is used to structure a distributed system with decoupled components, okay? So the components can interact with each other by remote service invocation, a broker, and a broker is responsible for the coordination, the communication among the different components. And so you see where clients request a service from the broker, and then the broker redirects to the client um, to a suitable service from its registry. So you see this in software applications such as Apache, Rabbit, JBoss messaging. Peer-to-peer, in this pattern, individual components are known as peers. And so peers may function both as a client requesting services from other peers and a server providing services to other peers. A peer may act as a client or a server or both. And so you see this in use cases such as file sharing networks, multimedia protocols, or what a hot topic nowadays, cryptocurrencies such as Bitcoin and blockchain. The event bus pattern primarily deals with events that have four major components. You have your event source, event listener, channel, and event bus. And so sources publish messages to a particular channel on an event bus, and listeners subscribe to a particular channel. Listeners are notified of messages that are pushed to a channel to which they have to subscribe to. So if you think about it, you use this on a daily basis because the use cases are notification services. You have your event source, and then you have your listeners, and you have your channels. And so you tune in and you get notification services. Also, Android development uses this model a lot as well. You have your Blackboard pattern. This is not Blackboard or like a Canvas shell or Blackboard knowledge sharing, but this is useful for patterns which there is no determined solution, okay? The Blackboard pattern consists of three main components. You have your global memory, which is the Blackboard, your knowledge source, which are specialized modules with their own representation, and then you have the control component, which selects, configures, and execute the models. So you see this in use cases such as speech recognition, vehicle identification and tracking, protein structure identification, sonar signals. The Blackboard pattern provides an effective solution for designing and implementing complex systems where heterogeneous modules have to be dynamically combined to solve a problem. Last, we have the interpreter pattern, which is used for designing a component that interprets a program written in a dedicated language. It mainly specifies how to evaluate lines of program known as sentences or expressions written in a particular language. So you see this in database queries, languages such as SQL, or languages used to describe some communication protocols. You can take a look at this and zoom in. These are advantages and different advantages of the several architecture structure patterns that I just talked about. But when you are looking to design an architecture, you first have to figure out non-functional system quality attributes, what your product contains or what you want your product to contain. Does it need to be responsive? Does the system return results to users in a reasonable time? Reliability, will the system features behave as expected by both the developers and users? Availability, can the system deliver its services when requested by the users? Security, you definitely want to protect itself and the user's data. Usability, can the system users access the features they need quickly without errors? Maintainability, can the system be readily updated with new features without additional costs? And then you have resilience. Can the system continue to deliver user services in event of a partial failure or external attack. So you have to consider these quality attributes when you're looking at your product to build your software architecture. Take 30 seconds to read this influence on architecture of a system security. The benefits of a centralized security architecture is that it's easier to design and build protection, and the protected information can be easily accessed more efficiently. However, if your security is breached, you lose everything. And if you distribute the information, it takes longer to access all the information and it costs more to protect it. If the security is breached in one location, you only lose information that you have in that one location. So that's all that we have for this lecture. We'll pick up in the next part of this lecture. So this is part 1 of this lecture series. I will pick up part 2 in the next one. Thank you for listening.